Hello, welcome back. Uh, I've decided, for your ease and my ease and just everybody's ease, to start just naming these videos the same as what the assignment is. So this is data representation number 3. It's going to go along with group work number 3 and practice number 3. Not surprisingly. What am I going to talk about today? Well, first off, it's Sunday and there's sun. I haven't seen you guys in the sun at the same time, so maybe that'll occur at some point. So this is obviously for uh, number 3 here. So let's look at number 2, some stuff from last time. There were some goofy graphs on passage number 2 from the homework. We'll look at those very briefly. Again, the structure of these videos is usually going to be, I look a little bit at the keys from last time's homework, going to walk through the practice, so I will walk you through practice number 3, just always yelling about the keys, making sure you're looking at them. If you're not changing your work, going back and modifying your work, your markups based on what the keys show, you're not doing what we're after here. I'm not grading your correctness in class like I normally would, because this is not a normal ACT prep class, but I'm not going to lessen the work on you. I expect you to do the marking up. So if you're not doing that, get on it, start making corrections to make sure that your markups look like my markups. Guys, look at my keys. They're good. Yeah. So we'll talk about practice number 3 and a couple things. There's like one really piece of prior knowledge you need to do the homework for today, and you need to know what momentum is. It's mass times velocity, but we don't even talk about velocity. We're talking about speed. So mass times speed, you're going to need that on the homework, and then where is p? We'll talk about that. So let's look at a little bit from homework from last time. So going back and looking at group work number 2, homework number 2. I know these files will say group work. I'm working at home by myself. Yeah, I'm sorry. It's the COVID's fault. First passage I thought was pretty darn straightforward. Pretty straightforward graphs. The only question I think people whiff on sometimes, they just think, I don't know what they do. Based on figure 1, the number of seeds that were dispersed per meter squared must have been at least, must have been what? You go back and look at figure 1 and you say, okay, well, I grew 7 red maples per square meter. If I grew 7 seedlings, how many seeds must I have planted? Think about that. If I grew 7 trees came out of the ground, I must have put at least 7 seeds in the ground because we controlled the plot. So 5D, 7 or greater, that one's a silly one, I always think. Passage 2, there's 2 goofy graphs you haven't seen here. A cumulative relative frequency graph and this segmented vertical bar graphs. Likely haven't seen graphs like these before. I wanted to talk about 2 questions in particular. Question 8 and question 9, greater than or equal to half a millimeter. Class and matrix figure 3. Well, here's figure 3. Here's half a millimeter right here, and this says, okay, half a millimeter and greater in size, that looks to be, what is that right there, 63 or so percent. So this is example 83 or accounted for 0.25 or greater. It told you how to read the plot. You had to do it for 0.5. And the other thing, number 9, it talks about at 270 kilometers, what is more than 50% by mass for class and more than 50% for matrices. You go to 270 and you say, what's taking up more than half of the bar? Looks like andesite right here. Looks like the slashy one, sand right there. Okay, so that's a couple questions I thought merited a little extra discussion from last time. People got on the Zoom and asked good questions. Mr. Bizzle asked some good questions last time. Get on that Zoom, ask me some questions at the end of class meeting. Every day, last 30 minutes of class, every day, get on there. So let's turn to practice number 3. I'm going to guide you through practice number 3, the first passage. You are going to hopefully do some timed work yourself on the second passage, and then we'll look at group work number 3. I'll at least vaguely gesture at it. All right, so one more time. These are the documents you should have in front of you. If you are at home today, I've already given them to you. If you are here in class today and I have not yet given them to you, please remind me to do so. Okay, so we're working on practice number 3 first, and then I'll gesture at some things from the homework that I think merit your attention. But once again, this science test is composed of passages, right? You're going to have 6 passages on this test, 35 minutes to answer the 40 questions. You got less than a minute per question. As we're getting deeper in, start thinking about your pacing. Last 2 days, I wasn't too worried about pacing, but we need to be moving at a rapid speed here. You know, a minute a question, that's not very much time. So I'm going to overlap these because you're going to need to be referencing back and forth, and let's get into it. So once again, if you don't have your colors out, go get yourself some colors, and I'm going to just rotate through and let's get after it. So let's start on number 8 here. Again, well, as I'm going back through, and where did these come from? This is, you know, April 2018. This is a recent test, and these are the 2 data representation passages from this test from a couple of years ago or so, right? So number 8 says, according to figure 1, so I'm going to put a box around that. It is telling me where to look at a temperature of 600 Kelvin. It's telling me where to mark on the graph. Which of some answer options, calcium, aluminum, and gold, have a resistivity, I'm going to circle that word, greater than 7 times 10 to the negative 8. I suspect the subscript or superscript isn't going to be that important. So we're going to look at figure 1 right here, just right above it. Let me zoom out a little bit so I can capture all of it. We're going to look at figure 1. We're going to say, okay, 600 Kelvin. So I'm going to take a little line, draw that up at 600 Kelvin. Which of those is greater than 7? And there is only one of those greater than 7. That is that guy right there, the solid line. What is the solid line? The solid line seems to go along with calcium. So which one is greater? That's going to be F, calcium only. Let's see if I can look at that side by side. Once again, if I'm ever going too fast, pause it. I talk fast, sorry. But you got a pause button because it's on YouTube. Number 9, based on table 1, make sure you're changing colors because I'm going to be marking all over this thing. Of the following 4 metals, which has the greatest ability to carry electric current? And then you might look over at table 1 and say, I don't see anything about carrying electric current. You may know that it's conductivity, but if you don't, that's a phrase that seems important to answering the question, for which you might do a little word search. Again, if we don't know what's going on, more often than not, I'm going to turn this so you can see me a little better. More often than not, the answer is going to be to do a word search. So yeah, that works. Okay. So let's look back for ability of a material to carry an electric current. Guys, it doesn't even change the words on you. Conductivity is what we're looking for. Of those 4, which has the highest conductivity? So we're looking at conductivity, greatest. I'm looking for the big number, guys. So beryllium, iron, magnesium, tungsten. So I got beryllium, iron, magnesium, tungsten. You need to be able to move pretty quickly through tables like that. I know that. You might say, oh, that was fast. Which one's the biggest of those? It seems to be up top beryllium. Do you have to know what beryllium is? No, it doesn't make any difference. These are just mystical words, and you're picking the big number that goes along with the correct mystical word. Let's keep it rolling. Number 10, according to figure 1. All right, so I'm going to be referencing figure 1 off here to the left. I'll zoom out a little bit so maybe I can get this all in frame. According to figure 1, approximately how many times as great, I'm going to circle the word as great there, is the resistivity of aluminum at 600 than at 320. So I'm comparing, you know, the resistivity of aluminum at 600. How does that compare to the resistivity of aluminum at 320? I have made up some abbreviations for what resistivity is. I know that that's not the real symbol, but it doesn't matter. You just got to write something down to conceptualize it for a moment. So let's take a look back at figure 1. Again, we're looking for aluminum. resistivity. And I'm going to look at 600 for aluminum. Okay, 600. Aluminum seems to be around 6. And at 320, if you didn't know where 320 was, you said that's 300, that's 400, and I got 1, 2, 3, 4, 5 steps. 100 divided by 5 steps, that's 20 per step. So let's go up from the first step, that would be 320. Take it over. How does 6 compare to 3? How does 6 compare to 3? It's twice as big, folks. So we were just looking up what was the number at 600 for aluminum, what was the number at 320, how did they compare? Twice as big. Okay, we're halfway through this first passage. Let's switch our colors, make sure we're staying on top of it. Look at the next one. You might look at the next one and say, man, that's the same. What's the difference between A and C? What's the difference between B and D? You need to notice, first off, good Lord, there seems to be some answer pairs here. Notice this is 10 to the negative 7th and 10 to the positive 7th. If I looked at that and said, damn, those are dang near the same answers. Look at what the difference is. That's what ACT is all about. Fiddly little differences that cost you $1,000 at this or that school. I know it's a strange game we play, but it's the game and I'm trying to help you make some money. So we're looking at those tiny little differences there. And then you'll notice you also have the 1.69 kind of pair and the 2.89 kind of pair. So we've got 2 different pairs of answers. Suppose that a certain metal has a resistivity of 3.46 times 10 to the negative 8. So that word suppose tells us we've got kind of a hypothetical situation. If you don't know what hypothetical means, what if? What if this happened? A hypothetical situation is what if? Suppose that this is true. What are the consequences of this supposition? That's a lot of words there. Based on table 1, the conductivity of the metal is most likely closest. Okay, so we're making a guess based on some info. We're making an estimate. Okay, so we need to look for a resistivity of 3.46. Okay, and I go over here to table 1, and I look, okay, 3.46. Well, 3.46 falls right between 3.56 and 3.36. Okay, that's cool. So what's its conductivity going to be? Well, the conductivity is probably going to be between those two, right? If the resistivity is between those two, then the conductivity is probably between those two as well. So I'm thinking, okay, what's between 2.81 and 2.97? I don't know, that's like 2.89. Then you got to look up here and see that it's 10 to the positive 7th. So it's 2.89, 10 to the positive 7th. Right away from the table, I kind of marked all over it, but that's a positive 7th. I'll turn my lamp on so maybe we can see a little better. That's a positive 7th. We can cross out the negative 7th answers and go with the 2.89 that the table seems to suggest. Do I know what any of that means? Not really. But that's what it asked me to do. It says, okay, well, if you got numbers here and here, what if we make you guess in the middle? Well, it's probably going to have in the middle sorts of properties, and that's what that question's all about. Number 12, 2 left to go here. When choosing a suitable metal for use in overhead electrical cables, think as you're driving along the interstate. Look at those big old cables carrying the power. Okay. Engineers prefer a metal for which the expression density times resistivity has as small a value as possible. So we want to make the product of those two things, we're called product, means to multiply, as small as possible. Based on table 1, which would be most suitable? That is, which one has the smallest density times resistivity? We're looking for which one has the smallest. You don't get a calculator. Ooh, that sucks. So we are looking then for this question to multiply these two together and see which one gives us the smallest product. We're going to do this for aluminum, copper, gold, and silver. So I'm going to do this for aluminum. a number a little smaller than 3 times a number a little smaller than 3. I don't know, I'm going to say like 8. So we can do it for aluminum. We can do it for copper. That's like a number that's a little smaller than 9, like 9 times 1 2/3. I know it's going to be 15. You could just double it and say it's going to be 18. It turns out no matter what rounding scheme you use, you're going to find the right answer. For gold, it's like 19 times 2, I don't know, 40 or something. And then silver, it's 10 times 1.5, I don't know, that's like 16 or something. You can see which one the answer is going to be. The answer is going to be aluminum. If you have just looked outside at those cables carrying the power, you might have said to yourself, well, it's not gold, and I don't think it's silver either. That doesn't seem reasonable. Copper, you ever looked at the Statue of Liberty? Copper isn't that shiny brown color very often. It oxidizes pretty quickly, gets a patina on it. It doesn't look that color. So the answer is aluminum. So one left, and then you guys get to do some practice on your own. I'm gonna do it for you. Number 13, based on figure 1. The resistivities of the metals listed in table 1. Okay, were most likely measured at a oh, I gotta go back and like figure out the temperature. All right, so I suggest here that I'm gonna have to combine sources. When it tells you about 2 different tables, figures, whatevers, you gotta put that information together somehow to answer your question. So it's saying, okay, figure 1, we don't know the temperature that this occurred at. We need to say, what temp did this occur at? Check that. What temp did those numbers from table 1 occur at? We have temperatures up here. We don't have temperatures over here. We need to figure out what temperature did this stuff get done at. We're going to figure it out from up here. All right, so, well, how am I going to figure out temperature? I need something that's in common between these 2 tables. And you might notice that calcium, aluminum, and gold, calcium, aluminum, and gold are on both tables. I notice that resistivities are on both tables. Resistivity. If I look that up for calcium, 3.36, aluminum, 2.65, and gold, 2.21, let's find where those values were over on this table over here. When is aluminum 2.65? Aluminum is the fine dotted line. 2.65 looks like right about there. When is calcium 3.36? Well, when is the solid line 3.36? I don't know, 3.36. That looks right about there. Oh, okay. When is gold 2.21? Gold 2.21. All 3 of these occur at a temperature of 300 degrees. So I had to match up the info I did have from the table, and see where the info from the table fell on the graph. And the answer there was B, 300 Kelvin. So that's that. Took a moment there. A lot of graph reading, a lot of connecting tables and graphs. Again, answers there are F, A, H, D, F, B. Keys are available on Schoology if my detail here is insufficient. But again, big ideas there. That suppose word, hypotheticals, and whenever we see 2 things mentioned, probably got to put that info together. Moving on to the next one, we got something talking. It's more chemistry. Talking about excuse me, pressure, boiling points and pressure. Talking about boiling points and pressure. We got some volatile solvents. Talking about their boiling points and pressure. So look what you can do. You can get your phone out, say 6-minute timer, start it, and try and answer these 6 questions. See how well you do. Pause your work right now. Pause. Okay, now that you've paused and done it, let's go back and work through this thing. Okay, again, most of these questions are going to tell us where to look, guys. That's why I spend so much time on these. They are essential that we get these right. Essential that we be able to use graphs to get answers. 21, according to figure 2, so we know where we're looking. Which of the following of the graphs best shows the boiling points of acetaldehyde? You don't have to know how to pronounce that. Acetone and pentane at 850 torr. Okay, so I'm going to look over here right next door, figure 2. 850 torr right there. Acetaldehyde, acetone, pentane. Let's draw it up. Who's on top? Acetone is on top. Acetaldehyde's on the bottom. Which one of these has acetone on the top? Tall acetone, tall acetone. Acetone is tall here, acetone is tall here. Who's on bottom? Acetaldehyde, that's got to be A with pentane in the middle. Okay. Top, middle, bottom. Not doing anything besides putting them in order. Look at these. It's just top, middle, bottom. That's all we're looking at there. So 21. First question is usually going to be pretty easy. First question is just going to be, hey, look at the data. Let's keep it rolling. 22. According to figure 3, 110 kPa. The BP of methyl acetate is approximately how much lower than the BP of ethanol? So we got to compare, at 110 methyl acetate to ethanol. So I go up here. Figure 3, 110. And I say to myself, okay, methyl acetate, ACE, how does that compare to ethanol? How does methyl acetate compare to ethanol? Well, let's look. At 110, methyl acetate is right around here at, I don't know, say 60. Ethanol right there, right about 80. So methyl acetate is 20 lower than ethanol. The phrasing of that was goofy, right? You could have crossed out the 10s for sure. You can see that these are 20 apart. But the way the question's phrased, you got to say, okay, it's this one compared to that one. It's methyl acetate compared to ethanol. 60 is what? 20 less than 80. Okay, that's goofy because of the way they phrase the question. Number 23, excuse me. According to figure 2, the BP of pentane at 700 torr is closest to the BP of acetaldehyde at which of the following pressures? So, okay, so let's find it. BP of pentane, 700 torr. That's what I know about. BP, that's right here. BP, pentane, 700 torr. Okay, that is right about there at 35. When does acetaldehyde get close to that? Well, when does acetaldehyde get up to 35? Here's the acetaldehyde line. If you wanted to keep that baby going, I don't know, it's somewhere out there beyond 100, beyond 1,000. It's got to go even higher. It never even gets there. So we better go with the highest option. We better go with D, 1,000 torr. That's extending the line out, saying when does it get there? Taking a look at this, you might be asking yourself, when does it get to that value? And it only gets to that value somewhere out beyond 1,000. 3 down, 3 to go. Then you guys get to do some homework. How exciting. Number 24. A compound's standard boiling point. Oh no, it's in italics. It's probably important. Look out. That's a new vocabulary word. That's an equal sign. The temperature at which the compound boils, atmosphere of 1 atm. Based on figures 1 and 2, the standard boiling point of pentane is approximately. Okay. So I'm putting together figures 1 and 2. And I gotta say, okay, 1 ATM. Well, what do I know about 1 ATM? All right, so here I got pentane down here, but I don't see anything about ATMs down here. I got pentane down here. Pentane's right here, but I don't see anything about ATMs. But I see ATMs up here. I got 1 ATM. Looks to be about 750 torr, something like that. Okay. Well, I can take that. I can take the 750, go up to pentane, and say, well, that's happening. Where's that happening? I don't know, like 36 or something. So what am I doing there? If it tells you about 2 graphs, take the information you know from one graph, convert it into units that you can use on the other graph. Notice that pressure in torr was the common thing that linked these two. That's the linkage. I took the ATM here, turned it into pressure, took the pressure here, turned it to boiling point. Look and always see what your answers are. If your answers are in Celsius, answer here, by the way, was G. If your answers here are in Celsius, you're going to get your answer from the Celsius side. But you say, okay, well, how do I get there? Got to be through through torr. How do I get to torr? From back up there at the torr ATM graph. 2 to go. 25, all right. Based on figure 1, pressure of 2 ATM would correspond to a pressure in torr. Oh, we just found that. We just found that 1 ATM was 750 torr. So 2 ATM, we can double. That's going to be 1,500 for 2 ATM. That's a really simple question. If you got the last one right, if you get 24 right, you're almost assuredly going to get 25 right. Easy question. I mean, really, if you see this and say, oh, 1 is 750, I can multiply by 2. That ain't hard. All right, now number 26 here. We got, suppose a sample of methanol is in a chamber maintained at 60 degrees Celsius at 110 kPa. All right, so let's go over there. Let's go to methanol and put a dot at 60 degrees Celsius, 110 kPa. So here's the methanol line. 60 degrees Celsius, 110 kPa, that's right there. That's that. Okay. I don't know what that means right now, but I'm going to put a dot there. Based on figure 3, if the temperature is kept constant, okay, so we're going to say temperature is kept constant, which of the following changes will cause the sample to boil? So it's got to be, when does something boil? Something boils if the temp is above the BP. If I make the stove, 150 degrees Celsius, the water's going to boil because the boiling point's 100. So I got to say, okay, what do I got to do to pressure to get this thing to boil? What did I say? I'm saying I'm keeping the temperature the same. It's going to be 60. I got to get it over here to cause it to boil. That's a decrease in 30 kPa. Decrease 30 kPa. That question's hard and requires you to understand boiling. Ever driven up in the mountains? Had that bag of chips expand? If you got less pressure pushing down on a liquid, it's easier for it to boil. That's what this graph shows here. If we were to decrease the pressure on methanol, the boiling point goes down. If we're pushing less hard on the methanol, it's easier for the methanol to leave. That's what that says. Answers there, A, F, D, G, D, F. A, F, D, G, D, F. You got a key online. You got two more passages to do for homework. Data representation group work number 3. I've got a couple questions I want to mention. Number 5. First of all, this is talking about a big old whale opening its mouth to eat some stuff. There's a video of it on Schoology. Momentum is mass times speed. If you didn't know that, now you know. Mass times speed. And by the way, that whale isn't gaining any weight, or not gaining much weight as it goes along. Number 11, I'm sorry for the poor quality scanned. It talks about point P. Where is point P? Point P is not on the thing. Point P is on the tower. Point P is up top where the thing starts. You got 2 passages, I think, what, 12 questions to work? Not too bad. Again, how long should 12 questions take you? 10 to 12 minutes. I know you're marking it up, so it's going to take longer, but you know, if we're reaching into 30 minutes to do these 2 passages, we are taking too long. Which passages or which questions can you skip? On the real test, you can guess on the ones at the end. For now, there's no guessing. All right, see you tomorrow.